Hello Legacy students, Marsh here. So today we're going to talk about E. Now, E is a really awesome letter, and he's a really cool letter that we relate to a lot in math. What you're going to want on you, your notes, calculator, you're going to definitely want like a scientific kind to find E, pen or pencil, and then you're going to need some graph paper. You're actually going to need 3 things of graph paper, not just 2 today. So, remember, you start talking about pi, probably in geometry, maybe even earlier, and what does it represent? Well, pi was, remember, the quotient between the circumference and your diameter. So we were able to find that it was related. It related a lot in circles. And we could simplify expressions containing pi, something like this. So 5 pi squared, that would have been 25 pi squared, right? Because you gave the pi squared in, just using our exponent rules. Pi to the -1 would move you to the top, right? Because you have negative exponents, it's going to flip around on your fraction. I'll simplify the 15 over the 20, and I would get 3 over 4, and then be pi to the 6th, right? Because the pi to the -1 would move up, become positive, so I'd get pi to the 6th. So now, guys, what we're going to talk about is what's known as Euler's number. And that's how you pronounce it. Kind of sounds like Euler's number. Now, Euler's number is approximately 2.71828. It's another really important number that happens in real-life situations quite a bit. And it's one of the numbers just along with like I and the pi. But E is what we're focusing on today. Now, you're probably saying, well, where'd this Euler dude get this number? Well, here's what he found out. That exponential growth formula that we looked at, the compound interest formula, well, what Euler started to do was kind of look at, well, what if we compound for each month? What if we compound for a year, hour? What about each minute? Well, what he started to realize is as he created those formulas and started computing the information, it got really strangely close. So I put my answers here for each of these. It started to get really close to Euler's number, or E, 2.718. And he went, that's kind of interesting. As I start to compound continuously, or as I basically just never stop compounding, I reach a, if you want to consider it a plateau of growth of 2.718. So he realized that that would be the growth amount. Thus, Euler's number was born. So, what we're going to want to focus on today is how do you simplify stuff with E, and also how do we graph things with E. So, first parts, let's simplify expressions. You're going to want to remember those exponent rules from long ago. So you're going to want to bring those up in the old noggin. Find those in there. Alright, so if you remember, guys, what you did when you had 2 of the same base multiplied, which is basically E, you added the exponents, right? So first things first, let's multiply the coefficients. So 2 times 6, that is 12. And then I'll have e to the -3 times e to the 5th. Well, I'm going to add the exponents. So it's going to be 5 minus 3, right? Or 5 plus a -3 if you want to consider it that. So it'd be 12e to the 2nd. Now, what is that approximately? Well, 12e to the 2nd, guys, is approximately 12 times 2.712 approximately to the 2nd. So it actually is 88.67. That is actually what the decimal approximation is that. Now, there is an E button on your scientific calculator, and if you need help finding him, usually he is the second key to the LN button. It says LN on it. It's right below log as well. So look for it. If you need help, I will help you find it when we get into class. So now I have 24e to the 8th divided by 4e to the 5th. So very first thing, let's divide the numbers. 24 divided by 4. Well, that's just 6, right? And then I need e to the 8th divided by e to the 5th. Now, if you remember, guys, what we did is we subtracted exponents when they were divided. So this would be e to the 8 minus 5, which is the same thing as 6e to the 3rd. Now, I did that quickly on my calculator, and I got 120.51. Okay, something to keep in mind just to kind of get a good guesstimate of what that actually means. Let's also find what this one is. So I got 4e to the 2x to the 3rd power. So remember, guys, when you had an exponent outside parentheses, we basically distributed, for lack of a better term, distributed it in. So we had 4 to the 3rd and e to the 2x times 3, right? So ultimately, 4 to the 3rd is 64, and e to the 6x. So you're probably asking, what else can we do with e? Well, we can graph e. Yay! We can graph e. So let us look. We got a parent graph of y equals e to the dx. Now we're still going to be making a table, just like last time. -1, 0, 1, and 2, just like when we were making those exponential graphs, because basically e, all it is an exponential. It just kind of looks a little different. So e to the -1 is 0.37. E to the 0 is 1. E to the 1st is 2.72. And e to the 2nd is equal to 7.39. So let's go ahead and graph those on my graph here. So I got -1, 0.37, 0, 1, 1, 2.72. It's like about right there. Oops. And then 2, 7.39. About right there. So if I graph him here, he's going to hit that die. He's going to start shooting up there. There we go. So notice, guys, this guy still has an asymptote at y equals 0 right there. This is a growth graph because it looks like from left to right it's going up. Asymptote located at y equals 0. Domain still -infinity to infinity. No changes there. But my range can't touch 0, but I do go to infinity. Now let's look at ones that have transformations going on. So my parent is still y equals e to the x. All we have is a stretch on this one and then also a shift horizontally. So let's go ahead and fill out our parent table here. 1, 0, 1, and 2. -1 had e to the -1 was 0.37. All I'm doing is on my calculator I'm typing e to the -1. E to the 0 is 1. E to the 1st is 2.72. And e to the 2nd is 7.39. So if I would graph those, graph my parent here, 0, 1, I don't think I'm going to fill in my line, but nevertheless, and then I'll go to 7.39 right there. So that is my parent. Change some color here. Okay, now I got to take care of my vertical stretch. This is my vertical stretch. Just like last time, since it is a vertical stretch, it's going to affect your y values. So I'm going to multiply every single y value by that value. So 0.37 times 2. My new table, x's haven't changed it a bit, but my y's I now have for -1 I have 0.74. I have 2 for 0. 2.72 times 2, that's 5.44. And then 7.39 times 2 is 14.78. So I won't be able to graph that dot any longer. However, it's still on my page. So -1.74, it's going to go right there. 0, 2, 1, 5.44, and then 2, 14, like right up there. Oopsies, up there. Notice, guys, though, this one still has a horizontal asymptote of y equals 0. It hasn't shifted up or down yet. Now let's go ahead and fill in our shifting. This is going to be a left 3. So basically I'm going to take all my purple dots and move them left 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Oop, missed that dot. So my black line, if I can erase everybody else here, there we go. My black line is my final answer for my graph. So if I look, it is a growth graph. My asymptote didn't move up or down, so it stayed at y equals 0. Domain, left to right, still getting all of the x values. However, my range, I am limited from 0, not touching 0, not including, that's why it's parenthesis, to infinity. Final one of the night. So e to the negative x plus 1. This negative right here, I know it's kind of freaking out because you're like, I've never seen a negative in an exponent yet, Marsh. What is that? It's okay. Your parent is still just y equals e to the x. So let's go ahead and fill out our parent table. Negative 1 was 0.37. This e to the first was 1, this was 2.72, and then 7.39. Just copying from what I've just recently used. Okay, now let's have a little sidebar conversation up here. E to the negative x. All that is a reflection. If it would have been negative e to the x, this would have been over x-axis reflection. That would have made it, instead of going like this, that would have made him go like that. That's a reflection over my x-axis. But this one, in this case, it's not affecting the y values. It's affecting the x values. Basically, it's going to negate my x values. So, let's fill in our new table here. I'm going to have x, y. So instead of being a negative 1, this negative, it's going to change it and make it a positive 1. This is going to flip us about our y-axis, excuse me. So it's going to be 0, and then I'm going to get negative 1 and negative 2. So I'm going to multiply basically these guys by a negative 1 continuously. My y values, however, they are not going to be affected at all. So let's go ahead and graph that. I got 1.37. So that's like right there. 0, 1, negative 1, 2.72, and negative 2, 7.39. Oops. So if I can graph it, it's going to be kind of weird going downwards. There we go. Notice, guys, this is a decay graph, looking left to right, which is kind of neat. If there's a negative in your x part right here, that's how you're going to know you're going to have a decay graph for ease. Good way to remember it. Now we got to move up 1 on each of our graphs. So up 1, up 1, up 1, and up 1. And with that, moving up 1, whoop, missed the dot. My asymptote is also going to move up 1, so my horizontal asymptote will be at y equals 1. As I said, this is a decay graph because left to right, notice it looks like a slide. My domain, negative infinity to infinity, but my range, we're getting anything from 1 to infinity. And that's the end of this video. See you later, Sabers.